Okay, so yes, I finished grading your exams and you should have gotten them back in your POs. And yes, like I said the other day, people did pretty well, including the version B people. Lots of A's. With the extra credit, the average ended up being pretty close to 90. And many people who didn't get A's got B's. So it was a pretty good exam overall. Back in your POs. What else do we have coming up here? We've got the project. I put the description on Moodle. Let's go through that now. I did say last night that you should decide on your groups by tonight at midnight. And you should form groups of 3 to 5 people and have one person send me a note. I will give you points for doing this. And to get full points, you need to send it to me by midnight tonight. Form groups of 3 to 5 people. They can be mixed with face-to-face and online. You're the same group on Moodle. The TAs don't even know who's online and who's in class here. So it can be a mixture. If you aren't comfortable finding or asking somebody, can I be in your group? Let me know about that too. Send me a personal email and I will try to find your group. But again, you should to get the full points, you should do that by midnight tonight here. Today being Wednesday, April 29th, 2015. All right, you're going to pick a lab from one of the ends of the first 5 chapters. The options are at the very bottom here. These are the possible labs that you can choose from. There's a lot of possibilities there. Once you've chosen a lab, you should read the lab by yourself. Then you should meet as a group to discuss the material in your lab. You should follow the directions in the lab and try to answer the questions that are stated in the lab. And then you're going to start to write up a report. And in addition to doing the lab, you're going to look for something that goes beyond the report, at least if you want to get close to 100%. Add excitement or go beyond. In multivariable calculus, when I have people do this, I have them do Mathematica beyond what is required for the basic part of the report. In this class, it's more flexible. You could use Mathematica to do something, to make a manipulate animation that goes beyond what's called for in the report. You could do an experiment, and people have done this in the past, do a physical experiment where you are trying to confirm what you see in the report. Does the math match the experiment, for example? It may or may not. You have to see. Another option is you could go and do some research beyond the basics of the report. You could find out about some other topic that's related to the report and add that extra bit of information into the report. There is an idea that you're trying to add some excitement to it. It's not just a dry report. You're trying to make it interesting. You should write your group report. You may use Mathematica to do so, meaning you may type it in Mathematica in text mode. You can add pictures into that. You can do the math in Mathematica. You don't have to, but you can. You may want to use different formats for the different sections. There should be a period here. You may also want to include appropriate graphs, but take note of the book's warnings that too many pictures is meaningless. You want to choose graphs wisely that really tell you some information that you want to get across. Each person will keep an individual timesheet, and we're not after equal abilities in your contributions, but we're after equal effort. Relatively equal in terms of the amount of time you put in. So each person needs to keep a track of the timesheet where you record your time that you spend on the project and what you do during those time periods. That's going to be part of your project. It should be very neat and detailed. And then finally, you're going to return your report, one report per group, by 9 a.m. on Thursday, May 14th. Okay, and you can email it to me. You don't have to make a printout. As far as the report description, I'm saying most likely it's going to be 3 to 5 pages long, but I have no official time length requirement. I only ask you to do an efficient and thorough job. It should have a nice title that should be in good taste. It should be appropriate to the topic at hand. You can create it if you want. You should have an introduction labeled with the word introduction. You should give the reader a basic feel for what the lab is about and why it's important. Maybe why it's interesting to you, why you pick it. There should be a main body of the report, which I'm calling discussion, where you describe what you did, what you thought about, and the calculations you did. Make connections to things you learned about. Highlight your main answers. You might want to use boldface type for your main answers. And you should have a conclusion where you summarize things and suggest other possible applications. Include bibliography if necessary. And again, to get up to 100%, your report should go beyond the basics of the lab in the book. If you just do the basic requirements of the lab in the book, you can get up to 90% on the report. It's worth 6% of your total grade. You'll be graded as a group, but it is possible that different people could get different grades. One way is with the timesheets. I'll look at your timesheets and compare them. Do you put in roughly equal amounts of effort? Not exactly necessarily. And I will also actually have you evaluate each other with a confidential evaluation, and I'll give you more information about that later. To make up for the time you're going to have to put into this, at a certain point, you're not exactly sure when, maybe starting next week sometime, as far as what you turn in, well, it'll initially be just completion, and then perhaps not even turning in anything into class, though there will be some problems to work on to study for the final exam. Okay, though I'm not sure exactly when I'm going to make those kinds of transitions. Any questions about that? So again, Thursday, May 14th by 9 o'clock, that's the due date time. You can certainly turn it in before that if you like. Send me a note if you have any questions. That includes the online people. Send me a note if you have questions. There's this extra reading to do, and some things you should know in this reading. Again, I didn't have time yesterday to go beyond the initial draft, and it's still not quite complete. I'm hoping later today I'll be able to complete it and post the updated draft on there. So there's a discussion about reviewing flows for linear systems. The title of this is Flows for Nonlinear Systems, Nonlinear Autonomous Systems, and some new ways to classify equilibrium points. Let me focus today just on what is hyperbolic versus non-hyperbolic. That's the easiest thing to get. Hyperbolic is a word that refers to, in our case, to equilibrium points. And I've got a definition of hyperbolicity, as well as a theorem, a rough statement of something called the Hartman-Grobman Theorem in this spot right here. Let's look at this definition right here. It says an equilibrium point for a nonlinear autonomous system, written in vector form, dy dt equals f of y, is called a hyperbolic equilibrium point. Hyperbolic equilibrium point if the Jacobian matrix evaluated at the equilibrium point corresponding to the linearized system near that point, or at that point, has no eigenvalue with zero real part. In other words, all eigenvalues have non-zero real part. Okay? So in other words, 0 can't be an eigenvalue. You also can't have purely imaginary eigenvalues to be called a hyperbolic equilibrium point. If you have one eigenvalue that's either 0 or purely imaginary, that's a non-hyperbolic equilibrium point. And by the way, I hope you've noticed that complex eigenvalues occur in conjugate pairs. If you get one, its complex conjugate is also an eigenvalue. And that occurs for purely imaginary ones as well. But anyway, again, to emphasize, if all the eigenvalues have non-zero real part, that's called hyperbolic. And if any of them have 0 real part, that's called non-hyperbolic. Again, I'm using this notation as far as the U goes, just to emphasize that in reality, when you consider this linearized system, this is a linear system related to the nonlinear system, that technically speaking, you're changing coordinates. You are shifting where the location of the origin is, so it's good to use a new variable name. U is the original variable minus the equilibrium point. That translates the origin to be at. In the new coordinate system, the origin corresponds to y0 for the original system. If you plug in y equals y0 right there, you get y0 minus y0, which is 0. You get the 0 vector. Why is hyperbolic versus non-hyperbolic important? Mostly because of this Hartman-Grobman theorem. It only applies to equilibrium points. And roughly speaking, this is not a precise statement, it says the flow of a nonlinear system near the equilibrium point can be related to the flow of the linearized system by a special kind of change of variable called the topological equivalence. We're not going to get into what that means. Basically, the idea is that it implies the flows behave in roughly similar ways. That's what we've been emphasizing with linearization. When you use the Jacobian matrix and you plug in the equilibrium point and you characterize the linearized system as sink, source, saddle, etc., that's telling you, in the case where you have a hyperbolic equilibrium point, that the nonlinear system behaves the same way near that equilibrium point, sink, source, saddle. Okay, it only applies to hyperbolic equilibrium points, though. The book discusses this. If you have a non-hyperbolic equilibrium point, if, for example, the linearized system is a center, then the nonlinear system doesn't have to be a center. Could be a center. Could also be a spiral sink or spiral source. You should make sure you look at the example starting on page 470 titled When Linearization Fails, and going on to page 471. Okay, it's an example showing that just because the linearized system is a center does not mean the nonlinear system is a center. It could be a center or a sink or a source. Though it will spiral, it will behave, the vector field is going to be similar near the equilibrium point, but whether it spirals inward, spirals outward, or is a center is very subtle, and so it could do any one of those things. Okay, so that's all I'm going to say about this today. We will come back to this more. In the meantime, you should read it. And again, I'll post hopefully a final draft tonight that would include more stuff in this section, this next section about asymptotic stability, stability, and unstable equilibrium points, which is a harder section. You got to think about examples. The definitions in there are pretty difficult to understand. But we're going to work at it as we've continually been talking about flows. Okay? This is an important thing to add, in my mind, to this class that we want to get to understand. So work at that. What are our main topics for today? I think for the sake of time here, I better start on the main topic of the next section, which is section 5.3. I do want to come back to section 5.2. I'm not sure if I'll have time today still. Go back to one of those competing species models, for example. May not have time today, may have to delay that for Friday. Instead, I want to focus on the harmonic oscillator again, and in particular the undamped case, and unforced as well. Then we're going to consider a slightly more difficult model. Actually, it ends up being a lot more difficult in some ways. Something called a pendulum, which has harmonic oscillator type behavior. It's a bob swinging back and forth. That's a pendulum. But there are some mathematical complications that occur that make it in some ways much harder than the regular harmonic oscillator in some ways. Related to that is a more general concept of something called a Hamiltonian system. So we better focus on these first to make sure we get these in. That's what your completion assignment is going to be related to. All right, undamped harmonic oscillator and unforced. Maybe I should put that in there as well. Back to an unforced, homogeneous, undamped harmonic oscillator. No damping either. Your basic equation is m times y double prime plus k times y equals 0. I'm going to use prime notations today to save some time from the Leibniz notation. All derivatives are with respect to time. That's m times a, the acceleration. The opposite of this, negative ky, is the restoring force from Hooke's law. No damping here, there's no plus b times y prime term. This, of course, is equivalent to y double prime equals negative k over m times y. And if we let v equal y prime, let v be the velocity, this results in a system that we typically write as y prime equals v and v prime equals negative k over m times y. And we've often called k over m cubed. Okay? There's no damping here, no friction. Therefore, some of you who are in physics should know that something is conserved. When you don't have friction, what is conserved? Conservation of what? You want to say it, Chris?
Momentum, energy.
Momentum is conserved, but energy is also conserved. Conservation of energy, mechanical energy, meaning kinetic plus potential. Now, when you've got friction, energy overall is still conserved, but some of it is converted to heat. So we're in the case where mechanical energy is conserved, no friction, an idealized case. The energy, I'll call it capital E, is conserved. What is the energy? Well, it's kinetic plus potential. I'll write potential energy first. What's the formula for kinetic energy? Physics people? 1/2 mv squared. It's a little harder. What's the formula in this situation, a harmonic oscillator for potential energy? Does anybody happen to know that one off the top of their head? For a harmonic oscillator?
1/2 kx squared.
1/2 kx squared, that's right. Or in this case, 1/2 ky squared. 1/2 ky squared, you could call it x as well. It's whatever variable name you're giving to your position. That's the potential energy for Hooke's law, mass in the spring. This kind of differential equation, a harmonic oscillator. What does it mean for energy to be conserved? This mechanical energy, this potential plus kinetic, to be conserved. It means, well, physically speaking, if you grab the mass, pull it, and let it go, it's going to oscillate back and forth forever and ever with the same amplitude. This quantity is going to be constant, and the constant value will be equal to, if you pull it and let it go from rest, whatever 1/2 k times the initial position squared happens to be. But these individual quantities will change over time. The sum is what stays constant. Is there a way to verify this mathematically? Yes, there is. If you differentiate the potential energy with respect to time along a solution curve, y of t comma v of t, energy here really is a function of y and v. If we differentiate this along a solution curve, I'm assuming this is a solution curve, we should get 0. Doesn't look like we're going to get 0, does it? We will if you think about it in the right way. How's the right way to think about it? First, use the chain rule. Use the multivariable calculus chain rule, which you can conceptualize like this. The energy, capital E, depends on y and v, the position and the velocity. And the velocity and the position both depend on time. The way to figure out the multivariable calculus version of the chain rule that will help us write this derivative in a certain way is to, along each one of these line segments, to write the corresponding derivative, the rate of change of the upper variable with respect to the lower variable. What's the derivative of y with respect to t? It's dy dt. I guess here I am going to use Leibniz notation. What's the derivative of v with respect to t? It's dv dt. What's the derivative of e with respect to y? It's de dy, although it's traditional to use partial derivative notation there, because e depends on y and v, two independent variables. Likewise along here, the partial derivative is de dv, using these fancy kind of these as your partial derivative indicator or operator. The way the multivariable calculus version of the chain rule works in this context then is to multiply the derivatives along each path in the diagram from the top variable to the lowermost variable that you're differentiating with respect to. So we have a dE dy times dy dt. And we have a dE dv times dv dt. Doesn't look like it's 0 yet. Keep going. What's dE dy? What's the partial of e with respect to y? Look at this equation. It's k times y. What's dy dt? Sounds difficult. I don't know what y is. That's okay. You do know dy dt equals v for all t along this solution curve. Go ahead and just put a v there. Ultimately, everything depends on t except for the k and the m. Although I suppose if we were thinking about relativity, even m might depend on t. Okay, no relativity here. Right? What's the partial of e with respect to v? Differentiate this with respect to v. Get mv. What's dv dt? Seems difficult. I don't know what v is. However, I do know dv dt satisfies this equation that it always equals negative k over m times y for all t. Again, I'm suppressing the t's in here. They should be in your mind. V and y depend on t. And look, like magic, the m's cancel. Then what's left over cancels, you get 0. kyv minus kyv. 0 for all t. Along a solution curve, along a curve satisfying the system of differential equations, the derivative of the energy with respect to time is always 0. The energy is constant. So E of y of t comma d of t equals constant along a solution curve. Different solution curves are going to give you different constants. Depends on that initial position where you let it go. Different energies. But along any given solution curve for a given initial condition, you'll have a constant energy. We're assuming there's no damping. Of course, in reality, there would be damping. Can we confirm this with DSolveValue? You have the generic initial value problem in there. There are formulas, somewhat complicated, but not terribly so, for the position and the velocity in general. Let's see if we can't confirm this conservation of energy in another way here. Let me type y sub k m y0 v0, making those all subscripts to emphasize that we've got 4 different arbitrary constants in here, though t is the ultimate independent variable. Just copy and paste this right there. Let's copy and paste this and modify the y to a v and replace the formula with this other one. Copy, paste. Plug these functions in. Get rid of that comma. And now let me also plug in a formula for the energy. I can't do capital E, because that's the number E in Mathematica. I could do little e. Little e of y, v. I guess it depends on k and m. I need a subscript there too. is, again, 1/2 ky squared, k times y squared over m, or 2, plus 1/2 mv squared, m times v squared over 2. What happens when I plug these functions into E? What happens when I evaluate E, the energy, sub k comma m, plug in these functions? Y sub k comma m comma y0 comma v0 of t, plug in the other one, which would be the v. What do I get? Doesn't look like a constant. Well, simplify it. It's constant, no t's. Okay, so there's another way you could confirm conservation of energy. Actually using the formulas for y and v. Over there, I never used the formulas for y and v. That would be a superior method if I couldn't find formulas for y and v, which will happen actually with the pendulum. I won't be able to find formulas. At least not simple formulas. This system is an example of what's called a Hamiltonian system. And the total energy is almost, not quite, but almost a Hamiltonian function for this Hamiltonian system. It's a constant multiple of the Hamiltonian function, in this case. The actual Hamiltonian function, we're going to take to be a little strange. H of y comma v, it's going to be in this case actually the energy divided by m. I'll show you why here in a second. In this example, it's the energy divided by the mass. For this example. It might not be that for other examples. Well, what is that all about? Why am I dividing by m? Hamiltonian systems have a special form. What is the simplified formula for this, by the way? Divide the energy by m, get 1/2 k over my squared plus 1/2 v squared. I claim that's a Hamiltonian function for the system. What does that mean? It means, coming back to the system here, that the right-hand side of the first equation is the partial derivative of the Hamiltonian function with respect to the second variable. Listen carefully. Some of you need to open your eyes. The right-hand side of the first equation, right there, is the partial derivative of the Hamiltonian function, I'm calling that capital H, with respect to the second variable. In this case, the second variable is v. Is that right? Yes? Take the derivative of h with respect to v, get v. 0 plus v. That matches that. And then the right-hand side of the second equation is the opposite of the partial of the Hamiltonian function with respect to the first variable, which is y. Is that right? Is negative k over m times y, is that the opposite of the partial of h with respect to the first variable y? Yes. Differentiate this with respect to y, that's a 0. This becomes k over m times y. Put a negative sign in front of it. You get that. So the reason we're dividing by m here to create this Hamiltonian function is so that this fairly simple relationship holds on the right-hand sides. You don't have to worry about extra factors. In general, when your system is written with x and y instead of y and v, dx dt equals little f of xy, dy dt equals little g of xy. That will be Hamiltonian if there's some function h such that the right-hand side of the first equation, f of xy, is the partial derivative of that function h with respect to the second variable. That doesn't match what happened here. It's just the roles of the variables switch. Back here, y is the first variable and v is the second variable. That right-hand side is the partial of the Hamiltonian with respect to the second variable. This right-hand side is the negative of the partial of the Hamiltonian with respect to the first variable. This right-hand side is the partial of the Hamiltonian with respect to the second variable, and this right-hand side has to be the opposite of the partial of the Hamiltonian function with respect to the first variable. So make sure you're careful about how you think that through, depending on how the variables are named. That's when something like that happens, when there is such an h where this happens, that's called a Hamiltonian system. And the Hamiltonian function, the h, is kind of like a total energy. Not necessarily exactly. In this case, it was the energy divided by the mass. It is a conserved quantity, though, just like actual energy is. If you differentiate capital H along a solution curve, using the multivariable calculus version of the chain rule, when you think of the variable relationships like this, again, assuming this is a solution curve, that is an important assumption. It's essential. Why is it essential? It's so that we can actually refer back to the differential equations and use the form of them to ultimately show this is zero. The multivariable calculus version of the chain rule says we can write this derivative like this. You can write that whether that's a solution or not. However, it's the next step. Where you are using the nature of the system. dx dt is dh dy. And dy dt, or dy dt is negative dh dx. Multiplication there. Get cancellation. This is 0 for all t. T is in the background here. In your mind, x and y depend on t. And so actually, ultimately, for this function, h depends on t. The value of the function h depends on t. You get cancellation, even though you don't see any t's down there. You get 0, but you should emphasize that's true for all t. And therefore, as a function of t, this thing is constant. Which has some important implications. The fact that the Hamiltonian function is constant means, it's another multivariable calculus thing, that solution curves have to lie on level curves of the Hamiltonian function. If you graph the level curves of h, the solution curves of the system have to be on top of those level curves. Let's consider this in the case of the pendulum. And let's derive a Hamiltonian function. Again, we're going to assume no friction, so energy is going to be conserved. I'm going to talk about the physics briefly, but not in enough depth that you're going to really get it real well, at least not today. Make sure you study the section to understand the physics too. You should understand how this is derived. It could be helpful for your project to understand how the physics is derived. So we have a pendulum. What you want to imagine with this pendulum is you have like a pin connected to a wall, maybe a long rod up here, so that the pendulum is away from the wall and will not hit the wall as it swings. And you don't want to connect it to the ceiling because you want to allow your pendulum to go around, actually, around and around and around if it wants to, right? If you give it big enough kick or something, big enough initial velocity, you can make it go around and around. There's your picture of a basic pendulum. You think of this as being a rod. So it's a thin rod, and it's got sort of counterintuitive properties. It's stiff, so it's not like a string. It doesn't get some slack in it. It's not like a spring either. It's a stiff rod, but it's got negligible mass somehow. I don't know how you'd make such a thing. This is where all the mass is. A ball, often called a bob, like a bobber for fishing maybe, a bob. You think of that as its name, bob. Okay. The bob is constrained to swing along a circle whose radius is the length of the rod, which I'll call capital L. It's constrained to swing along that circle. We're also going to draw a vertical line here and call this angle theta, and theta will be measured positively if you're in this kind of position to the right of the straight downward position. If the angle's over here, it can be measured negatively. And this arc length here, we're going to call S. S is a standard unit, letter to use for arc length. What are the forces that are applied to this bob? Well, there's certainly gravity. F grav. There's another force, heads up this way, essentially is the force that keeps the rod the same length and keeps the bob moving along the circle, even with gravity going on. I don't know what to call it, a tension force maybe? Does that sound good? F sub tension. I don't know if that's the best name. Those two forces add together via the parallelogram rule to give you the main force you need to think about for the motion, which is this one. I'll just call that F. And do a little geometry. This angle's theta, so this angle is going to be theta as well. And then you can use some trigonometry to say the magnitude of F, which I'll write like that, is m times g times sine theta. Sine theta is opposite over hypotenuse. The hypotenuse is going to have length m times g. It's the length of that vector there. That's the magnitude of this force. It points in the opposite direction as the sine of S. S is positive in this direction. So ultimately, Newton's laws, Newton's second law in particular, F equals ma, gives you a differential equation that basically looks like this. M times S double prime equals negative mg sine theta. That's a second order differential equation related to the motion of this pendulum. It's got two dependent variables in it, really. It's got S and theta in it. They are related. S is L times theta. The length of the rod times the angle ends up equaling the arc length, if your angle's in radian measure, which we're assuming. L is constant, so the derivative of S with respect to t is L times the derivative of theta with respect to t, and the same kind of relationship holds for the second derivative. That allows you to replace S double prime with that. The m's can also cancel in this undamped case. If there's damping, the m doesn't go away. But in this case, you can write the equation like this, and ultimately write the equation like this, if you like, as a second order equation. The thing that makes this equation difficult, and in some ways much more difficult than the simple harmonic oscillator, is the sine theta. If that were just a theta, essentially it's the same as the harmonic oscillator. But it's not a theta, it's a sine theta, and that makes it more difficult to find a full solution for this thing. And basically, impossible using techniques you know. We can still write this as a system. It's a second order scalar equation as it stands by letting v equal theta prime, the velocity, angular velocity really, in radians per unit time, like radians per second perhaps. That leads to a system. Theta prime equals v. V prime is theta double prime is negative g over L times sine theta. There's a first order system. But again, it's a nonlinear system. The sine of theta here makes this nonlinear, and since that's a sine theta instead of theta, it's a nonlinear system, which makes it more difficult to deal with. We can still draw the phase plane, however, and we can still find the equilibrium points pretty easily. Look at this system. What are the equilibrium points going to be? Set the right-hand side equal to 0. That forces v to be 0. You're not going to be at equilibrium if the velocity is non-zero. So the velocity has to be 0 at equilibrium points. You're also at equilibrium when the sine of theta is 0, which occurs at theta equals 0, straight down. Occurs at theta equals pi, straight up. If somehow you can perfectly make the pendulum straight up, it will stay straight up. But nobody can really do that in practice. It'll be 0 when theta is 2 pi, which is the same position, really, the same physical reality as theta equals 0. Mathematically it's different, but as far as the physical reality goes, it's the same initial condition. Theta equals 3 pi, 4 pi, 5 pi, 6 pi, or going back to theta equals 0, go in the other direction, theta equals negative pi, negative 2 pi, negative 3 pi, negative 4 pi. There's infinitely many equilibrium points in a theta v plane. And they're all along the theta axis. Mathematically, there's infinitely many of them. Physically, there's really only 2. Straight down, straight up. There's periodicity in the mathematics that's related to treating the physical reality differently. What does DSolveValue produce here with this pendulum? Let's see. Does it produce anything? Notice how I'm typing things in here. I'm typing the system. Theta prime equals v. V prime equals negative g sine theta over L. I do need to put a theta over theta of t in there. This system is autonomous. When you write it by hand, there's no t's on the right-hand side. The vector field in the phase plane will be constant. It will not be a moving vector field, which is certainly simpler to think about autonomous systems. But with Mathematica, you've got to put the dependence on t in there to emphasize that theta and v are functions of t. What does DSolveValue produce? It seems to say it can't do it, which is strange because it worked on my computer. Sort of. I'm making a mistake compared to what I did in my computer. Let's try a particular initial condition, like theta of 0 is pi over 4 and v of 0 is 0. Let's see if this works. Okay, that sort of worked. This was the type of output I got for the first one on my computer, I thought, unless I just was remembering wrong. Okay, there's the answer. Ha ha ha. We're really going to use that. Arc, cosine, inverse function, elliptic f, imaginary units, arc sinh, square roots, yikes. Okay, so it evidently has some formula, though it does involve non-elementary functions. Elliptic f is a function you've never heard of before. Maybe you could use it, get Mathematica to use it, but it seems like we probably want to go with using NDSolve or NDSolveValue. And as I've said before, even though NDSolve is harder to understand than NDSolveValue, because you have to add the extra evaluate and the slash dot inside the plot like this, it does seem to be easier to work with if you want to change your initial conditions. Oh, I forgot to enter this first. Here we go. So the locators initially on the point whose coordinates are theta is pi over 4, v is 0. So that's a 45-degree angle. The pendulum is about like this, and I let it go from rest. What happens? Well, you don't see the phase plane in the background. You don't see the direction field. We can figure it out without that. Go back to the system here. V is starting at 0, so theta prime initially is 0 at time 0. Theta is starting at pi over 4. Sine of pi over 4 is positive square root of 2 over 2. You're going to get a negative quantity here at the initial condition. V prime initially will be negative. You let it go from rest, it's going to start to move to the left. So in this picture, the solution curve is going to go clockwise. I put the direction field in the background, we can see that. It looks like a periodic solution, which should make sense because there's no friction. Seems like maybe it's on an ellipse, but here appearances are deceiving. That looks like an ellipse, but it's actually not. And it becomes more pronounced as your initial angle goes closer and closer to pi radians. You can definitely see it's not an ellipse there. And watch what happens once you go past pi. That happens so quick. See that? When you go past pi, it flips. In the phase plane, in the math, the solution does sort of change to being in a much different spot, although physically, it's not doing much different. Theta equals 2 pi is right about there. That corresponds to the same position as theta equals 0. So mathematically, it looks different, but physically, it's doing something similar. But again, that's not an ellipse. You can definitely tell that. And even when it looks like an ellipse, it's actually not. Just looks like it. Watch what happens if you give it a real big initial velocity. What's going on there? The velocity stays positive. It's an angular velocity in the positive direction, which is counterclockwise. It keeps going around and around forever. If I continue this to the right, it would keep going like that forever. Looks like a cosine wave or something. It's not. It just looks like one. Okay. Is energy conserved? How are we doing on time? Oh, getting low here. Is energy conserved? Yes. Is this a Hamiltonian system? Yes. Let me quickly find the Hamiltonian function. Can I find a function capital H that satisfies these conditions? If I can, then this is a Hamiltonian system. Essentially, I have to find it by integration. Integrate this thing with respect to v. Get 1/2 v squared. Integrate this thing with respect to y. Excuse me, theta, sorry. Theta is the first variable. Integrate that with respect to theta, get plus g over L cos theta. All right. I guess so. This thing is a Hamiltonian function. Now, finding the Hamiltonian function is not always that easy. You can't always do it by guessing. The book's got harder examples that you should study, where like the variables could be in both. It could be in both the right-hand sides, both variables. And it's a little tricky that way. There's also a condition in the book that guarantees you got a Hamiltonian system. Most systems are not Hamiltonian, by the way. For most systems, you will not be able to find such an H. And if you try, it won't work. If the right-hand side of the first equation only depends on the second variable, and if the right-hand side of the second equation only depends on the first variable, then it will work. But if you've got mixtures, typically it won't work. Okay, the book talks about that too. Before I put this on Moodle, I will have Mathematica draw the level curves of this function in the same phase plane with contour plot. Curves where this function is constant, and you will see the solution curves will be on top of those level curves. Also very important to know that. Okay, we'll talk about this more on Wednesday or Friday. See you then.